In this video, we're going to solve some exponential equations. We're going to express irrational solutions in exact form and as a decimal rounded to 3 decimal places. Now in the first two, we'll be using this property of exponentials. So that's this property here. We have a base b taken to the x power and set it equal to base b taken to the y power, and b is positive and b is not equal to 1. Then it'll be true that x is equal to y. If b to the x is equal to b to the y and b is positive, b is not equal to 1, then it'll be true that the exponents will be equal. So for the first one here then, we have 5 to the negative x is equal to 25. So we try to use this property. We need to have the exponents the same on both sides. So got 5 to the negative x, and 25 is the same thing as 5 squared. 5 is positive, not equal to 1. So if we can get the base the same on both sides, the exponents have to be equal. So negative x has to equal to 2. Multiply through by a negative tells me that x has to be negative 2. You put a negative 2 where the x is, and you get a negative in front there. That gives me a positive 2. 5 squared equals 25. You can easily check it. So that's the exact solution there. Now for number 2, we can use the same property for this one, because 8 is the same thing as 2 to the third power. Got a base of 2 here and a base of 2 there. So the exponents have to be equal. X minus 5 has to equal to 3. Add 5 to both sides here. Get x is equal to 8. You can check it here. Put an 8 where the x is. 8 minus 5 is 3. That's 2 to the third is 8. Checks out. Now for the third one, 2 to the x is equal to 10. I can write 10 as 5 times 2 or 2 times 5. But there's no way I can get the same base there. So in this case, I can't use this property. So what I have to do then is use something like this. I can take two ways I can work this. I can take the log of 2 to the x, and that'll be the base 2. And then I do the same thing on the right side. Log of 10 to base 2. So here I have log 2, log to base 2 of 2 to the x. These bases are the same here. That just gives me an x. Or another way I could do this is I can say, well, using the property of logs, I can take this exponent x in front here, be x, and then it'd be log of 2 to base 2. Log of 2 to base 2 is 1 because 2 to the 1 is 2. And that still will give you an x. But if these bases are the same here, the answer is just whatever the exponent is. So x is equal to the log of 10 to base 2. Now I can say, okay, this is my exact answer. That's one answer I can give. But I also want an approximation to 3 decimal places. This is one exact answer here, and I can say, okay, this is equal to, using the change of base formula, I can say, well, take the log of 10 to another base. You can use base 10 or base the natural log e, because that's what your calculator has. So I just say this is the log of 10, and then it's the natural log of the base there, it's 2. Now I could also use this as my exact answer. I can avoid this and just take the natural log of 2 to the x and then natural log of 10 and solve it. But in this place, in this situation, I use my calculator then. So it will be natural log of 10 over the natural log of 2. And I get this right here, 3.3219. and run that out to 3 places at 3.322. So I can say, like I said, exact answer would be log of 10 to the base 2, or I could even use ln of 10 over ln of 2. So for number 4, you can see the base on the left side is 3/5 taken to the 3/5 is the base taken to the x power. On the right side, the base is 7. Again, there's no way I can get the base the same. So when you got something like this, the only thing you can do is take the log of both sides. You can use any base you want. Log to base 10, natural log. And for these types of problems, it's either going to be the natural log or the log to base 10. I'm going to choose natural log, so this will be ln of 3/5 taken to the x power, and that's going to equal to natural log of 7 taken to the 1 minus x power. Then I'm going to use properties of logs. I have 3/5 to the x. This is going to come out in front here, so that's going to be x, and this will be ln, or natural log of 3/5. On the right side, again, same property. This exponent will become a coefficient, so I'll just put it out here, 1 minus x, and I'm left with the natural log of 7. Then I'm going to multiply here on the right side. Let me write this down here. So it's x natural log 3/5. Multiply here by natural log of 7 on the right side. So it's be natural log of 7 times 1 is natural log of 7, and then times the minus x will give me a minus x natural log of 7. I want to solve for x, so I want to collect my x terms here. So this will be x ln 3/5, and bring this over to this side. So this will be plus x ln of 7. I'll leave the ln of 7 over here on this side. So I want to solve for x. So on the right side, or on the left side I should say, I'm going to factor out an x, and in parentheses I'll have ln 3/5 plus ln of 7. And that's going to equal to, on the right side, ln of 7. Okay, now here in the parentheses on the left side, still got the x here, I got the sum of two logs, ln of 3/5 plus ln of 7. So one of the properties of logs allows me to write that as a single log. We just multiply the values. So 3/5 times 7 is 21 over 5. And this is equal to ln of 7. So now I just divide both sides by ln of 21 over 5. This will be x should equal to ln of 7 over ln of 21 over 5. And 21 divided by 5 is 4.2. So I could give this as my exact answer here. ln of 7 divided by ln of 4.2. So this is my exact solution. And then to get the approximation, or round it out to 3 places here, I go ahead and use a calculator. ln of 7 divided by ln of 4.2, and to 3 places, this will give me 1 decimal, 356. So this is the exact answer here, one form of it. I could leave this as 21 over 5, but since 5 goes into 21 without rounding off, leave it as a decimal. I would leave it this way, but you could leave it as 21 over 5 here. That's exact. And this is your decimal approximation. Thanks for watching. We'll see you next time.